There's only 2 questions. Let's have a look at page 11 of your worksheet. So let's just have a look at page 11. Okay, page 11 is June 2017 P41. June 2017 P41 would be this one. Hey, sorry. This one concerns Brownian motion, which I haven't covered with you. There's one small part in the notes that I haven't covered yet. Okay, right. Now, if you look at the first question, part 4a, they're asking you describe the motion of molecules in a gas according to kinetic theory of gases. So how does a gas molecule actually work according to how does a gas molecule actually move according to kinetic theory of gases? So what was mentioned to you was that the molecules are in constant random motion. If you recall what was written inside the notes, it was mentioned that the molecules are in random motion. They are in constant random motion. So you can say that they are in constant random motion with a distribution of speeds in different directions. Okay, so this question actually has 2 marks. First mark is for you saying random motion, and then second mark is actually you saying that they are in different directions. Okay, but you want the statement to be complete, you just say molecules are in constant random motion with a distribution of speeds in different directions. This will make your answer more complete. Okay. So this is kinetic theory of gases, which describes to you the motion of gas molecules. Now, because you say that these gas molecules are in constant random motion in different directions, there is one particular experiment that actually proves you that there's an experiment that proves to you that gas molecules actually move in constant random motion in different direction. So that experiment that proves to you that is something called Brownian motion. Okay, so describe what is observed when viewing Brownian motion that provides evidence for your answer in A. So if we know that gas molecules are in constant random motion in different directions, the experiment to prove to you that is something called Brownian motion. That one is actually under page 3 of your notes. So if you look at page 3 of your notes, so Brownian motion experiment proves to you that gas molecules are in constant random motion. So what specifically is Brownian motion in the first place? Brownian motion is actually just the random motion of small particles that are caused by the bombardment of other molecules. Okay. What's so important about it is that it gives you evidence that air molecules move randomly in all directions with a range of speeds and kinetic energies. Okay. So when you're talking about Brownian motion, the example they always use is this. They tell you, you go and trap some smoke particles inside a smoke cell. So what they do is that, maybe I better zoom this thing in. What they do is that if they want to view Brownian motion, what they'll do is that they have a smoke cell. This is what we call a smoke cell. It's basically a glass cell that's filled with smoke. Okay, so in addition to the smoke, there's actually some air inside also. So what they'll do is that once they trap some air and some smoke inside the glass cell, they will shine some light through the glass cell or smoke cell. And then after that, what they'll do is that they'll use a microscope to view inside the glass cell or inside the smoke cell. So what they can see is that the smoke particles, which are bright specks of light under the microscope, are actually seen to be moving about in a haphazard or random manner. Okay, so the thing here is that your glass cell contains smoke particles and air molecules right now, but when you try to view it under the microscope, when it's being illuminated by light, the smoke particles are the only ones that you can see. They are normally seen as just some bright specks of light. Okay, but the air molecules themselves cannot be seen, even though you're eliminating the glass cell or smoke cell. Okay, so when they were looking at the smoke particles itself, which is actually this little, not this little, this big thing here, what they saw was that smoke particles is actually moving about in a random haphazard manner, like the ones that's being shown in your diagram right now. Okay, so the thing is that why is it that the smoke particle moves like that? Why is it moving in a haphazard and random manner? So what they say is that the smoke particles move like that, not because they were colliding with each other, but rather it seems to be more on the fact that they were being collided upon by some other invisible particles inside the smoke cell. Okay, the reason why they move like that wasn't so much so because it was colliding with other smoke particles. It's more due to the fact that they were knocked about by some other invisible particles. So the invisible particles that we're talking about here is actually your air molecules. Okay, and because you see that the smoke particles are moving in a haphazard manner like this, in a random manner like this, they actually came to the conclusion that the air particles themselves must be moving in a random manner. It's because the air molecules move in a random manner. When they collide with your smoke particles, they cause the smoke particles to move in a random manner as well. Okay, so that's why we say that Brownian motion gives you evidence that air molecules, or rather gas molecules, move in a random manner. They move in random motion. Okay, so if you refer back to your question, describe what is observed when viewing Brownian motion that provides evidence of your answer in A. What can you see from Brownian motion that told you that gas molecules are always in random motion? So you say something like this: the small particles, which are seen as bright specks of light, move randomly in a zigzag motion. That's what you just need to say. Okay. All right. So this one should be all right. Okay. Now this is what Brownian motion is now. Okay. Brownian motion is still inside your syllabus, but it's not something that they frequently ask. It will come out rarely. That's why you see out of all the ideal gas questions we've done, this is the only instance where Brownian motion came out. Okay, now moving on to part C. At a pressure of 1.05 times 10 power 5 Pascal and temperature of 27 degrees centigrade, 1 mole of helium gas has a volume of 0.024 meter cube. The mass of 1 mole of helium gas assumed to be an ideal gas is 4 grams. Calculate the root mean square speed of an atom of helium gas at a temperature of 27 degrees. So this one, they're not asking you for the mean square speed. They want specifically root mean square speed. Okay, so when it comes to this question, you want to find the root mean square speed. Usually it's either PV equals to 1 over 3 NMC square or half MC square equals to 3 over 2 KT. You can use either one of these equations to find your root mean square speed, but let's just do one of them first. If I use half MC square equals to 3 over 2 KT, is half times M. Now, M is actually the mass of a gas molecule. All right. Right now, you see that there is a value for mass here, 4 grams, but this is actually not the mass of one molecule. This is the mass of the whole gas itself with N molecules. Okay, it's not the mass of one molecule, but rather it's the mass of the whole gas with N molecules. So you want to find the mass of one molecule, logic will tell you that M would be M total divided by number of gas molecules. Okay, so you will actually take 4 grams, but remember to change it to kg, so you times 10 power minus 3 divided by the number of gas molecules. Here, they already told you that this 4 grams is actually for 1 mole. So we know 1 mole is actually having 6.02 times 10 power 23 molecules. So what our substitute here for number of molecules is 6.02 times 10 power 23. So your mass of one molecule is this. Then multiply with mean square speed, then equate it to 3 over 2 times K, which is 1.3 times 10 power minus 23, and then multiply with 27 degrees Celsius. Remember to change to Kelvin by plussing 273 Kelvin. Okay, so your mean square speed is going to be this value, 1.87 times 10 power 6. Find the root mean square, you just square root it. You're going to get the answer is 1.37 times 10 power 3. Okay, now this one is if you're using half mc square equals to 3 over 2 kt. You could have actually used another separate equation also if you wanted to. You could have also used PV is equals to 1 over 3 nmc square, which gives you your mean square speed. So here, this one might actually be easier actually. P is your pressure, 1.05 times 10 power 5. Your volume is 0.024, which they've given you here. Equate it to 1 over 3 times 4 times 10 power minus 3 times mean square speed. Now, your Nm, by now you should know is actually the mass of the gas, no? Which is actually your total mass. No? Okay, so here is 1 over 3 Nm, that's correct, but Nm itself, you know, is going to be 4 grams because that is the mass of the gas, that's the total mass. Okay, so you actually just sub it as one single value. Eventually, you get your mean square speed as this value, then square root 8, you're going to get this. The answers are exactly identical. All right, so just use whichever you like. All right. So Nm is mass of gas, is mass total. You can also say it's actually the mass of whole gas with N molecule. They all mean the same thing. All right. Okay, so this one is fine. Then after that, moving on to part 2. Move to part 2. Use your answer in 1, which you just found, to calculate the root mean square speed of atoms at 177 degrees centigrade. So same thing as before, 27 degrees centigrade change to 177 degrees centigrade. You want to find the root mean square speed, find out an equation that kind of relates them together. Now you won't use PV equals to 1 over 3 nm c square here, because you see you have information for temperature. This one has no T, so you won't use this. The only thing that you know that has mean square speed and has T inside is this. Half mc square equals to 3 over 2 kt. So same thing, this equation applies to both these cases. What is constant for both of them? You know that m and k is constant. Therefore, mean square speed is proportional to t. So mean square speed 2 to mean square speed 1 is equals to T2 over T1. So mean square speed 2 over mean square speed 1, which is 1.87 times 10 power 6, is equals to the ratio of the temperatures. Change them to Kelvin. 177 plus 273 divided by 37 plus 17 plus 273. This is the value of your answer. Okay, 2.805 times 10 power 6. Then square root it, you're going to get 1.67 times 10 power 3. Okay, so this is your answer. Right, so there's one last question that is in page 8, but let me see whether it's a repetition or something that we've done. And next one is page 8, all right? So let me just clear off everything here. You can just have a look at page 8 first. Let me see whether page 8 is something different. Okay. Why can't I change? Okay, page 8 is actually something different. We'll just go through that. Okay, it's not something we've done. The calculation is not something we've done before. Okay, just go to page 8, June 16, P42. We'll finish this, then after that we'll go on to a new chapter. This one should be question 2. All right. So state what is meant by your Avogadro constant. Is a definition for your notes. It refers to the number of atoms in 12 grams of carbon-12. Okay. You need to state specifically is atoms, okay? Because carbon is made out of atoms, not molecules or particles. It's specifically atoms. So it's number of atoms in 12 grams of carbon-12. And then what is a mole? This is definition of unit, okay? 1 mole is the amount of substance containing 6.02 times 10 power 23 particles, okay? This one is unit definition for amount of substance. Okay. Now, moving on to part B. Part B is saying that you have a container of volume 1.8 times 10 power 4 centimeter cube. The ideal gas in the container has this pressure at this temperature. Show that the amount of gas in the cylinder is 150 moles. So this one pretty straightforward. Amount of moles, amount of gas. This one is talking about amount of moles, the number of moles, sorry. You just use PV equals to nRT. Pressure, 2 times 10 power 7 times volume, 1.8 times 10 power 4 times 10 power 6 because you want to change centimeter cube to meters cube. And then N times 8.31 times with temperature in Kelvin. So 17 plus 273. So at the end, you will get number of moles as 150 moles. Okay, so this one is pretty straightforward. Okay, C1. This one is got a bit different. Now you look at C1. They're telling you that gas molecules leak from the container at a constant rate of 1.5 times 10 power 9 atoms per second. The temperature remains at 70 degrees centigrade. In a time of T, the amount of gas in the container is found to be reduced by 5%. Now calculate the pressure of the gas after time T. Okay. So if you think of it this way, this one is your before case, this is your container before, and then this is your container after. All right. So right now, there are a few things that you can actually deduce. This one will be P1, B1, N1. P1, B1, T1 for N1. This one will be P2, B2, T2 for N2. Okay, now number of moles is actually not the same here, unlike the previous examples you've done, because they specifically told you that there is a leak inside your container that caused the number of gases to reduce. Hence, your number of moles will reduce. So what they did tell you is that the amount of gas in the container remaining is actually reduced by 5%. So you can actually say that when you go from here to here in the time of T, N2 is actually just going to be 0.95 of N1 because you lost 5% of it. Okay, but are there anything else that has changed? Volume by right would not change because you see your volume, your container, it has a volume of 1.8 times 10 power 4 here, right? Your container is assumed to be a rigid hard object. Okay, so if you have a lid inside your container, the volume inside the container itself by right would not change. And we know that gas will always fill the volume of your container containing vessel, right? So here, volume actually did not change. I can say that V remains constant as volume of containing vessel did not change. Okay, the containing vessel volume did not change. So the gas that fills out the container, its volume will not change too. So volume is constant. And then after that, they also mentioned to you this temperature remains constant at 17 degrees. All right, so you can then say this, no? If you look at PV equals to nRT, V is constant, R is obviously a constant, T is also a constant. So that would mean that pressure is actually just directly proportional to your number of moles. Okay. So wait, let me just write something here. This one B remains constant as volume of continuous vessel did not change. Then T remains constant at 17 degrees. Okay. So if I know the pressure is directly proportional to number of moles, that would mean that P2 to P1 is N2 to N1. Okay. So P2 is the ratio of N2 to N1, which is 0.95 N1 over N1 times the pressure at 1, which is actually what I have here. 2 times 10 power 7. So you multiply them together, you're going to get the answer as 1.9 times 10 power 7 Pascal. Okay, so this is your final answer. Right, so this one, no issues. Then after that, we move on to the last question. Okay, zoom up. Okay. Now, then after that, what they want you to find after that is the time t. When your number of gas molecules reduced by 5%, or your number of moles reduced by 5%, how much time did it actually took to reach that value? They want you to find the time taken. Okay, so recall that they actually gave you this information. Number of molecules released per second is actually 1.5 times 10 power 19 per second. So what you want to do is you want to find out the total number of molecules released. You can actually just find out the total number of molecules released first, which you know is going to be 0.05 of N1. Okay, because they told you that 5% of your gas molecules has been released, or rather 5% of your number of moles has been released. So it will actually be 0.05%. Okay, total number of moles. Okay, now maybe I just rewrite this. The total number of moles released is 0.05 N1, which is 0.05 times 150. So therefore, number of molecules released is going to be 0.05 times 150 times 6.02 times 10 power 23. Okay. So this is basically what we are trying to find out. Okay. We know number of molecules released per second is this value. We know the total number of moles released is this value, but I'm interested in the number of molecules. So I take whatever I just found, number of moles, multiply with Avogadro constant. So to find the time taken, this one, I'll just write it here. Therefore, time taken T is going to be 0.05 times 150 times 6.02 times 10 power 23 divided by 1.5 times 10 power 19. Okay, this is one way of looking at it. The working that I wrote here is actually kind of the same, but somehow or another people don't seem to get it as much. Here, number of moles released is 5% of 150, 7.5 mole. My release rate, meaning to say the number of molecules released per unit time. I think this is the issue that's causing the misunderstanding for most people. Release rate relates to number of molecules released per unit time. So which would be number of molecules released divided by time. So just sub in your values and you get the answer. So T is 3.01 times 10 power 5. Okay.